Hello, everybody. Welcome to this guest lecture, which is part of Advanced Topics of Software Engineering. It's my great pleasure to have Len Baas with us today. Len has been in the computing industry for about 60 years or so, he keeps saying. And he'll talk about that as sort of a second talk, the last probably 20 minutes, 30 minutes. And before that, he'll talk about AI engineering, developing software for AI that gets actually deployed into production. That is based on a book that we recently wrote that will come out in probably February next year. So Len is an eminent figure in the software architecture field. He has looked at various subfields of computer science over the years. He spent his academic career, actually, I don't know exactly where you started it, but his first big position was as a tenured professor in Rhode Island. And he gave that up to join the Software Engineering Institute of Carnegie Mellon University. So he spent 15 years in Rhode Island, around about 25 in Carnegie Mellon. Then he came to Australia, which is where we met for around about 3 years. We were colleagues there, wrote a book on DevOps, and Len has been writing more books on DevOps now since. And then he's, of course, very well known for the books Software Architecture and Practice, now the most recent being the 4th edition, right? Okay, so yeah, it's a great pleasure to have you here. Thank you for joining us, Len. And let me just switch over the.
Oh, is it? Yeah, this works. Okay. So I am assuming that software architecture and practice is a required textbook for this course. So as Ingo said, I'm going to talk. I have two talks. So the first one is technical information, and then the second one is just after 60, it really is 60 years. So I got a bachelor's degree in mathematics in 1964, got a job as a programmer. And so I will talk about some lessons that I've learned over the 60 years. But let me start by talking about AI. Okay. Okay. So AI as a field sort of got started about 1958. There was so there is a funding agency as part of the United States government called DARPA, which is Defense Advanced Research Project Agency. It still exists. They decided that the military in the United States needed to learn something about AI, so they brought together a whole bunch of people. No one knew what AI was. We're talking 1958. And so everybody was all excited. Look at this. Look at the opportunities. The Turing test was sort of what they were aiming at. And so in 1958, Herbert Simon and Alan Newell, both from Carnegie Mellon, by the way, said that within 10 years, a digital computer will be the world's chess champion. So they were a factor of 4 off. Not too bad, actually, if you think about it. But it didn't happen until 1997. The thing is that people are still incredibly optimistic about their AI projects. So this year, Iran Corporation did a study where they interviewed, I don't know, several thousand executives, and they came to the realization that somewhere around 80% of AI projects don't actually go into production. Now, you might, if you have any experience, what you might say is, well, there are a lot of projects that don't go into production, and that's certainly true. There are a lot of reasons why things do not go into production, but that's about twice the rate of non-AI projects. So what I'm going to speculate on is the causes of that, and then how you deal with those. So the first cause I want to talk about is the fact that when you build a normal software system, a non-AI system, it doesn't, sound stupid, doesn't have any AI part. When you deal with an AI system, you get involved in system engineering types of activities as opposed to software engineering types of activities. And so the AI, in an AI application, the AI portion is just part of the system, and there are all these other parts. But if you look at the AI portion, it has two parts. So there is a knowledge base and an inference engine. So we're decomposing the AI part, the decomposition of the non-AI part. I don't know if you've looked at it, at any of the software architectures of large system, Netflix or Google or any of those kinds of things, you can kind of imagine what the rest of this looks like. And if you look at how it gets developed, you have a set of developers who deal with AI. Those are the data scientists, and they deal with data, and they have a bunch of tools to help them. And then you have a bunch of developers who deal with the non-AI portion, and they have a bunch of tools to help them as well. Okay, so one of the changes that I've seen in 60 years is the number of tools that we're okay. The number of tools that exist in the field and in supporting. Now it's much better, right?
There we go.
Okay, so the number of tools that exist. So one of the things I've learned about in 60 years is that when you stop a sentence and somebody interrupts you, just remember the last word that you said. And when Ingo mentioned that I was at Rhode Island and I ended up teaching the same course multiple times. And there, one of the things I would do is I would walk into the classroom and I would say, okay, what was the last thing I said? And then I would pick up again. That's one of the reasons I left. Okay, so the developers also use tools, and the number of tools that exist in the field is even in the non-AI portion is in the order of hundreds. My guess is that the number of tools that exist when you in the software development field these days is now well over 1,000. Okay, so part of what you should be learning is what are these tools? What do they do? Uh, um, how do you decide which tools to use, which tools are appropriate for which purposes, and so on and so forth? I'm not going to talk about that. The other thing that happens is if you look at this picture, we have the data scientists and the developers. And what that means is that you have a interdisciplinary team. And that's because there are a lot of disciplines. It's very difficult for one person to know everything. And so what happens in a team is that you pull together people that have specialties and then they have to work together. And it isn't as easy as it sounds. So if you go into industry, they say, okay, what we'll have is some sort of interdisciplinary team. We'll take people from here, people from there, and they'll be productive. That doesn't work that well. So there's a theory. You have power struggles, you have vocabulary problems, you have resistance to change. Okay, you end up with one discipline. So software engineers should be in charge, right? I mean, we all agree with that, except for the data scientists and so on. And this requires a certain amount of education. So there is a vocabulary issue. Uh, the vocabulary for artificial intelligence is different than the vocabulary for software engineering is different than the vocabulary for DevOps. So if you look at the word performance, Performance to a software engineer means latency or throughput, efficiency. Performance to an AI person means accuracy. How good is the model? How correct are its answers? Performance to a DevOps person means how fast can I get things into production? Okay, so I mean, just that one word in those different disciplines has different meanings, and there's a period of time that it takes to build a team. And so Bruce Tuckerman, some long number of years ago, uh, talked about team formation, and he talked about forming, putting the team together, storming, the team fights, norming, they decide how they're going to actually operate, and then performing, they're actually producing things. So as soon as you say you're going to have an AI portion of a large system, you now have to deal with the issues involved with teams, the issues involved with disparate tools, and the issues involved in the manipulation, excuse me, the manipulation of the data and the manipulation of the software. Okay, so right away it's pretty broad. So I sort of wanted to call on people. It gets to be hard in this kind of setting. So anyway, let me call you sitting there by yourself. um, so how do you package an inference engine? How do you put it together so it talks to other pieces of software? You have any idea? No, but if you had a piece of software, how do you package it to get it into production? You talk about containers? Not yet. Okay, no questions. So what happens is that the AI portion has to be compatible with the non-AI portion. It has to be compatible in terms of being able to send messages to communicate with it. It has to be compatible in terms of how it's put together. It has to be compatible in terms of how you're going to put it into production, how you're going to actually deploy it. Okay, so let me move on to the next one. Maybe I'll hit some discussion questions that somebody actually knows the answers to. So that's my style of teaching these days. So I require that everybody looks at a video about the lecture, so I don't stand up in front of, this is boring, I don't stand up in front of, slides. The presumption is that they've looked at them, and in order to enforce that presumption, I give them a quiz. So they have to take a quiz over what they were supposed to learn. And whether they get it right or not doesn't matter that much, but the fact that they have to take a quiz acts as a motivation. And then they come in and I say, okay, tell me what you learned. Could you kind of elaborate on that? And then we go around, we have a discussion. I find that much more interesting than actually standing up and lecturing. Okay, so the second part of the problem. So we talked about interdisciplinary and the fact that you need to take a system engineering approach. There is inherent uncertainty in AI systems. It's all probabilistic based. I'm not going to talk about rule-based systems, which are deterministic, but in general, these days they're all probabilistic. And so there are two types of AI, really. There's what used to be just machine learning, and then over time it became narrow machine learning, meaning it's a specific task that you're building the system for. And then there are foundation models, which are your favorite AI assistant, ChatGPT or Gemini, or you guys use Claude. And so anyway, there are a number of them. And you can get them to fight with each other if you want. It's always an interesting exercise. And so narrow machine learning models are used to support particular tasks. and I'll talk about what they are. Foundation models are called foundation models because they have no specific task designation. They're intended to be general purpose on which you would build a task superstructure. And so narrow machine learning models are statistical. They're intended for a specific task. And the data that you use is labeled data. So are people familiar with a regression? If you do a linear regression, is that an assumption I can make? Okay, so if you have a bunch of data points, 2 dimensions, you put it on a plot, and you say, I want to draw a line that goes through it. That's a type of machine learning model. So what you get out is a formula that says, I want to take the x value and multiply it by this coefficient, and it will result in this y value. That'll be a point, hopefully somewhere near the line. So what you're doing is if you give it an x value that isn't in the plot, you're predicting what it's going to do. That's a type of machine learning. Okay, so that's a specific task. Regression is a specific type of model. And the values that you have labels. You have independent variables. These are the ones that you have no control over. You have dependent variables. These are the ones you're trying to predict. Example I gave you, you're only trying to predict one. It turns out you may want to predict more. You know, so you can have multiple independent variables and multiple dependent variables. And you can use more than a line. You can use polynomials. It gets very esoteric very quickly. But the output is a generated value. Okay, label. The important thing is the data has labels. It has meaning. So if I tell you what's the correlation between the number of students in what's the gender distribution of this class? I have an individual. They have a gender. I get a percentage, and that would go into my training. Okay, so it's concrete. And the one example is a spam filter. So you provide a whole bunch of independent variables to the spam filter. You know, there's an email message, the sender's email, the recipient's email. I was just saying, just yesterday, I got a message saying that I don't know if people know what the disease Ebola is, but it's a very contagious, deadly disease. I got an email message from the university nominally saying that there was a case of Ebola on campus. About 4 or 5 hours later, I get a message from the university saying, no, that was spam, somebody trying to get your credentials. So their filter was good enough to recognize it. And there are a number of things. And the output is spam or not spam. Again, a label. Is this spam or not? Input is labeled. So here is the message. Here is the sender's email. All of those are specific values. So what happens with the narrow machine learning models is there's a bunch of data that goes through a bunch of tools. The knowledge base is external to the system that you end up with. But the inference engine is part of the system you end up with. And let me use the idea of drawing a line again. So you characterize a line. They should know this, right? You characterize a line by knowing its slope and its intercept. Is that too esoteric? So that's 2 values. It has a slope and an intercept. Given the x value, you can use the slope and the intercept to predict the y value. Okay, that is the inference engine. That's the computation part. The fact that I got that line by looking at 10,000 data points is the knowledge base. So that when I get around to executing the system, I only need to know the slope and the intercept of assuming I'm using the linear regression. I only need to know the slope and the intercept in order to get the value. So that's a very small set of numbers. Okay. And so the knowledge base is outside. You keep track of it for various reasons, but it is not part of the system that you're producing. And what are the narrow ML models are used to have three main purposes. So you can classify something is spam or not spam, any kind of classification. You can do regression, which is a prediction. Given this set of independent values, what is the likely dependent value? So classification might be you're a good credit risk. I'll give you a credit card. Or you're a bad credit risk. I won't give you a credit card. So that's a kind of classification. Um, my credit card company is on the ball. When I charge something in Germany, what happens is I get an email or a message from the credit card company saying this charge was just made on your card. Was that you? And so, I have the opportunity to tell them no, and they'll turn off my card, which, I don't want to have happen, so I don't say anything, even though it was me. And so the second purpose is regression, and then the third purpose is clustering. I have a group of customers. I'm Netflix. I want to know which customers like this category of movie, which customers like this other category of movies. And so I cluster them based on what they've been watching. Okay, so that's again an application of a narrow machine learning model. And if you get into this, there are probably at least 2 or 3 dozen different types of models that you can use. It's just enumeration. And that's part of what data scientists are supposed to know. And as software engineers, you just have to trust them. So what are the problems? There are ethical concerns. How do you explain the answer you got? I got turned down for a credit card? Come on. My credit's perfect. Overfitting means that I have a line that goes through all the points. Well, if I get some point that wasn't in my original data set, the line likely isn't going to go through that and the prediction may be wrong. So overfitting means that I have not enough parameters for the data, or too much data for the parameters. I don't know, whichever way it goes. And then you can attack it in a variety of ways if you're interested in security. So let me go into that. So how do you deal with bias and ethical concerns? Well, all these models are trained, right? We had a set of data, it went into the model, and where does the data come from? Oh, the data typically is historical data. Okay, well, historical data is going to reflect existing biases. So you need to worry about correcting for biases and ethical kinds of behavior, because the data you get may have been gathered over a period of time when social norms have changed. So all of you are too young, but there was a time when a woman was not eligible to get a credit card in her own name unless a married woman. She got a credit card in her husband's name. Not that long ago. Well, certainly in my lifetime, so within the last 30 or 40 years. Okay, well, that's changed. Okay. But if your data that you use to train the model goes back that far and reflects that kind of bias, then the model will inherit that bias. Okay, so you need to worry about having a training data set that actually represent what you want to have happen. Now the basis is going to be historical, more than likely, but you need to adjust it. You need to make sure, well, that's what I just said. There are organizations that are putting out ethical frameworks. Let's see if I can get the acronym right. The OECD, the Organization for Economic Cooperative Development. Does that sound right? Something like that. You can has what they call an ethical framework for AI. You can look it up and it'll tell you what to worry about. Organizations get measured in some sense based on how ethical their decisions are. And so organizations have established ethical review boards. Okay, so you're a bank, you have a system that does loan approval. Is this system behaving appropriately? You have to convince an auditor, more or less. So you're the developer. You have to convince an auditor, more or less, that this in fact is behaving responsibly. So the auditor comes with this framework. Bank has added some additional things to the framework, and you have to convince the auditor. Okay, so that's an ethical review board. And then there are tools that you can use to help you detect bias. And what happens when you look at these tools is you get involved in statistical methods. And for no particular reason, I fell in love with the term Kolmogorov-Smirnov test. Uh, that's a test that lets you tell whether two populations are the same. I just like the way it rolls off my tongue. It's not that I know anything about it or who Kolmogorov or Smirnov was. I just like the sound of it. Okay, so how do you deal with interpretation? So what happens is that you get rejected for your credit card. And your natural question is why? Okay, well, the computer told me not a good answer. Okay, and so what you want is to understand the reasoning that the computer has. That's explainability. And there are a couple different techniques that you can use. I'm not going to go into them, but everything. So machine learning has been around for 20 years maybe. And there are dozens of techniques. And they all have names. And so then after a while, when you have a name, you make it an acronym, and then you learn the acronym and you forget what the name is. But anyway, here are a couple techniques that are called explainable. They help you explain things. Another one is let me do the same model without one of the variables. I'll just remove that variable, go through the same process, compare its predictions with the predictions of the full model, and I get an understanding of how important that particular item that I'm leaving out is. That's called feature importance. How do I deal with the fact that I may have not enough data to do a good job of training? Again, overfitting. And how do I keep particular data points from overwhelming the model? So if you are looking at average age in this class, and I happen to be a student here, all of a sudden the average age gets very much larger than it would be without my existence in the class. And so that is an example of a particular data point skewing an average in some sense. And so there are techniques for doing that. Regularization is one of them. Let me do some cross-validation. Let me add data. Data augmentation says I'll add data to get rid of some of this skewing. And there's a technique called feature engineering, which again incorporates this. And one of the things I learned when I got into this is there's something called hyperparameters. So a parameter for a model is a value you put into it. A parameter for a software module is a value you send to it. A hyperparameter controls the parameters. So to put it in software engineering terms, you have to send a valid type. If you have a strongly typed language, you have to send a valid type to the procedure you're calling. That's the types that are valid are hyperparameters for the procedures, for the procedure calls. They control the procedure calls. So you have to have a list of these hyperparameters, of the types that are valid, before you can verify that the types you're doing are valid and do the kinds of translations that are necessary. So you take that and you put it in AI model terms, and now you have hyperparameters, and you can juggle those in some sense. So that's another way of dealing with generalization and overfitting. You can attack these models, some of them. So you get into supply chain issues. Where does the data come from? What's its lineage? Did we have a bad actor somewhere in the process of collecting data? So this is pretty extreme, but I made a movie. Nobody watched it. I get into the Netflix database and I show that it's the most popular movie for 2 weeks. All of a sudden it gets recommended to a bunch of people. Okay, so that is an example of an adversarial attack. You're deviating from reality in some way. There are a whole variety of these kinds of things. So and you can train your model to learn to recognize these and to ignore them. So you can do adversarial training. You can validate your input, especially if you're dealing with a large language model or something like that. Okay, you need to be careful how you input things. You can inject noise. So in software engineering, there's something called fuzz testing. Again, so what that means is you have a system, you give it data that isn't correct, and you would like the system to reject the input. So you do fuzz testing. If it doesn't reject the input, then you would like it not to misbehave, at least. It may take the input, but you don't want it to misbehave. Okay, so there's the equivalent with these models. And again, if you have a interdisciplinary team, the software engineers, understand testing mechanisms, may understand fuzz testing, understand sanitation. The data engineers will have different names. So one of the things that happens is that you are creating a field or you're new to a field and you see some phenomenon and you make up a name. Well, it turns out that somebody made up that name, a name for that phenomenon some time ago. Now you have two names for that phenomenon, and maybe yours catches on and the old one gets lost, or maybe they both catch on. Okay, so one of the things you need to worry about as part of this team formation is making sure that everybody's on the same page in terms of what the words mean, what words you use to describe what phenomenon, and so on. And then it turned the world is concerned about AI systems. And these concerns are showing up as regulations. Okay, so I mentioned ethical frameworks. There are laws. There's the GDPR. Okay, so that's in the European Union, that's the law. Right? It's not just a regulation, it's a law. Is that right? Yeah. So the difference between a regulation and a law is a regulation is something the government says, a law is something the parliament says, more or less. Sometimes a regulation is an interpretation of a law. Anyway, there are laws coming out to govern AI and regulations coming out to govern AI. So I talked about an ethical review board. They ought to pay attention to these kinds of things. And so you need to have lawyers look at the things that are coming out. So maybe a lawyer isn't part of your team, but a lawyer might be part of the organizational structure. And so they need to know that the world has changed in some sense. Okay. So that's sort of what I'm going to say about narrow machine learning. Uh, Foundation models are relatively recent, the last 5 years now. And in this case, the knowledge base is part of the system. And the inference engine is part of the system. So you can access the knowledge base. Well, it depends on the, I shouldn't say that. It depends on the particular model. Uh, but what happens is that these foundation models have two parts to them. So first, what are they? They're trained on massive amount. I'm sure you all know this one. They're trained on massive amounts of data, billions, maybe trillions of pieces of information. Takes massive amounts of computer power to do the training and to access them. Uh, and the data is unlabeled. So the fundamental difference between machine learning models and foundation models is that the data in machine learning, and there's some exceptions, but is by and large unlabeled data. I mean, is labeled data. The data in foundation models is unlabeled. Here's a bunch of text. Figure out what it means. That's kind of a task for in the foundation model. I'm not going to tell you. And then there are ways of fixing that up. But they're intended to be general purpose. And then large language models, I'm sure you're familiar with. So they're used for all kinds of things. This is actually an area of research. Let me extend the use let me explore the use of a foundation model in this particular domain. And sometimes it works and sometimes it doesn't. But they're used for natural language processing. They're used for translation, text to machine. They do summarization. They'll make up stories. I don't know. Again, you ask it to write a. So I have a friend who used to be an archaeologist in. I got the right domain. Archaeologist in the Peruvian desert. So I asked my friendly AI assistant to make up a story in the style of Edgar Allan Poe. And if you don't know who he was, he invented horror stories back in the 1800s. Uh, and so it came up with a story about this guy that dug up a skull and the skull became alive. And my friend that had dug in the Peruvian desert said it didn't have the ring of truth to him. But you can ask him those kinds of things. So it makes up stories. They're good at summarization. Here's a bunch of stuff. Boil it down because I want to use it for a quiz answer, that kind of thing, and some other things. But the interesting, at least to me, the interesting part is the transformer architecture. And there are two key concepts. One is called a vector space. So visualize a space with 10,000 dimensions. Every word, although they're not words, think of syllables, I guess. Every syllable is one of the dimensions. So if I'm going to process a billion pieces of text, there are a lot of words in there, and there are a lot of syllables, but they may mean the same thing. Some of them or look at the same. So the example that you see frequently is the word book. What does a book mean? Well, a book can be a collection of paper things bound together. You can get a book of stamps, different notion. You can make book if you are a gambler. Okay, so the word book by itself, without any context, will be a point in this vector space. And there will be adjustments to that vector space based on the words that came before it. So if I say a book of, or the words that are around it, it's context. So if I say a book of stamps, then what will happen is the place in the space that relates to book will get moved over to the place in the space that's close to book and close to stamps. If I say make book, then will get moved to a place that's close to book and close to gambling. Okay, so the vector space has the notion of distance and you can move things around. And then once you've done that, now you want to talk about the relationship between the various types of sentences. So what we've done with the moving things around in the vector space is we've gotten a word and maybe a couple adjectives and some relationships. But how does that relate to the other words in the sentence? And that's the attention mechanism. And if you look at that, it's god awful complicated. You're manipulating matrices that are 1,000 dimensions. So one of the things you'll see from the hardware manufacturer is I want to build a chip that can multiply a 1,000 by 1,000 matrix quickly. And from a software perspective, how do I tell the chip that it's about to multiply two matrices and feed it the matrices as opposed to one at a time? So, the way you multiply two matrices is a row by column. You don't want to do that item by item. You want to do that all at once. And so the hardware manufacturers are making chips that can do that quickly. But then the software people have to feed the data to these chips in the right kind of way so that they can actually work at speed. Okay, and that's all part of the attention mechanism. Not going to go into that. Once you have a foundation model, how do you make it task specific? And how do you customize it? And so in general, you customize things by adding context information to the input that you give it. So there are a variety of ways of doing that. And again, to go back to my example of this archaeologist in Peru, I would add context to say he did his digging in 1836. Okay, and it would know what was going on in that period and feed that into the story. So that's adding context. And you can add context in a general way. You can add it through the prompt. So I said, write a story. Okay. And then I added the context in the style of Edgar Allan Poe. Okay, so I'm giving it more directions. You can add context from supplemental data storage. So I have a database out here that has a lot of information in it. And I will retrieve that information based on some of the keywords in the query and add that to the query to the foundation model so that it has an appropriate amount of context. And that's called retrieval augmented generation. So what are the problems of data models or foundation models? How are we doing here? We have data privacy as a problem, security is a problem, exposing sensitive data, misinformation is a problem, and then fake contact. And I got a little thing here. It'll go away. Okay. And in general, what you can do with foundation models is put what are called guardrails there. So I love computers. So a guardrail is, as its name suggests, it looks at your input query and makes sure that it's legitimate according to some criteria. It looks at the output and makes sure that it's legitimate, again, according to some criteria. So if you sit down and you ask ChatGPT, tell me what you know about, and then you put in your name, it'll come back and say something like that's personal information. I can't do that. However they phrase it. And that is a guardrail that looked at the input, said you're asking about a particular individual. This individual is not a famous individual. So if you ask it, tell me all about, I don't even know who Chancellor, I was going to say Angela Merkel, but I'm way out of date. But whoever the Chancellor is these days, it'll look in this augmented reality, into this context information, find out that Angela Merkel, in fact, is a real person who's famous enough to have queries about her. And so it has to make that kind, the guardrail has to make that kind of decision. So you put a guardrail in front, so it looks at the, and it can be very sophisticated. You put a guardrail at the end, so it looks at the output. Okay, we're not allowed to produce nudes, so it looks at the thing and says, you know, is this a Greek statue? Yes, nude's okay. Not a Greek statue, nude's not okay. Again, they get fairly sophisticated, and it'll block it. Okay, so a guardrail is I don't want to say the basic way that things are prevented, but it's certainly widely used. Okay, I don't want to do discussions. And then the third thing I want to talk about is that if you're a software engineer and you've read the textbook for this class, right, the software architecture and practice, you know that the architecture is determined by the quality attributes. So you have a collection of quality attributes. They reflect the business context of the system that you're building. People, it's very rare that systems get built for fun anymore, especially sizable systems. They used to, but that was relatively small. So a big system is built by a bunch of people. They expect to get paid or to make money out of it. I don't know why. Karl Marx probably wouldn't approve of this. And so the business has to decide it's going to invest in this system. So they say, we're going to sell this system to people, or this system's going to have these properties. Security is important. So now you say security is important. Performance is not so important. You know, we're going to do batch processing, so we don't have to worry about interactivity too much. So that goes down. I think what I'm going to do is change this system, just throw it away in 3 years and rebuild it. Okay, because the world will have changed enough. So modifiability goes down. Or I want this system to live for 20 years, in which case modifiability goes up. So you have a list of qualities that you want to achieve. They reflect the business goals. And that is what quality is for non-AI, is done for non-AI systems. So what do I mean by quality? It's fitness for use. Okay. And it's characterized by quality attributes. So performance, security, reliability. It may be that reliability is important to your business goals. It may be that it's not. Okay. I can tolerate the system being out of service for a certain amount of time. Or I can't. And it depends on what you're trying to do with the system. And it's determined by the software architecture. Again, there are ways of achieving particular qualities. It's determined by the development processes that you use. You want to test for these qualities. It's determined a little bit by code quality, but actually less so than you might think. And if you have AI systems, you've added another facet to this. Again, another complication, and that is the quality of the model. And the quality of the model depends on which model you're using. If I'm doing a line fitting and my data is all over the map, then I'm not going to get a very good line. So I need to use a different kind of model. And it's determined by the data. How good is the data? And data quality is very important in getting quality of the resulting system. So you want to have a certain amount of training data. 10 times the number of parameters is sort of the recommended value. So if I'm just doing a line, it's only got 2 parameters. I only need 20 points, right? 2 times 10, I can do that. If I'm doing a polynomial, then it gets to be more. If I'm doing one of the more sophisticated models, it gets to be more. Distribution of the training data, I talked about that. Okay, you want the training data to reflect the kinds of data that you're going to input into it. and the results to reflect the kind of data that you're going to input into it. And that may or may not be historical data. Typically is based on historical data. And you want to adjust it to reflect security. So image recognition can be distorted by just changing a few pixels here or there. And if you have an automobile and it's looking for a stop sign, people have done experiments where they put a little sticker or something on the stop sign, and it's not recognized anymore. And so the data that you've trained the system on may not reflect what's happening. So if you look at housing prices, and I trained it on a set of housing prices over the last 10 years, and I happen to live in Munich, housing prices only go up. That seems to be the phenomenon. So the data that I trained it on is going to become out of date as the housing prices rise and so on. Maybe the world changes. We have some sort of environmental change. Okay. And the model wasn't set for it. So I want to use I did this model for Munich. I want to use it for what's a small town around, for some rural area. It won't work. It'll give you the wrong answers. And maybe somebody passed a law. Maybe there's a new regulation. Okay, that will cause problems with the data that you have. And again, you need to monitor that kind of thing. So while the system is operating, now we get to Kolmogorov-Smirnov. While the system is operating, you want to test the incoming data, the distribution of the incoming data against the distribution that it was trained on. How do you do that? Well, you run it so you know what the distribution of the incoming data is. You have to have saved the training data so that you can do this comparison. The training data comes from a whole variety of problems or sources. I may have gotten the training data off the web. I may have gotten the training data from some sort of fitness thing. I may have gotten the training data from going to a doctor's office. I may have gotten the training data from doing a survey. What happens in the survey when people don't respond? Okay, so what you do is you have to adjust all the data in one way or another. That's part of preparing the data. It can cause problems. Okay, so part of what goes into the data is what's called the lineage. Where does it come from? What's happened to it over the course of being put into the model? What experiments did I run on the model? What tests did I run on the model? And so on. You need to keep track of all that. And so at runtime, when you're running the system, you can check. Okay, and again, there are statistical techniques to do that. Somehow AI has become a full employment guarantee for lawyers. Okay, so if something goes wrong, who are you going to sue? Right? I mean, you have to talk to your lawyer to find out who's liable, and then you can sue them. And so organizations have lawyers who look at what's going on. And some organizations have lobbyists that go to the parliament and advocate for certain types of rules and regulations. Maybe the model you're using isn't correct, doesn't do a good job. So you want to change the model. How can you change the model without having to change the rest of the system? This is an architectural problem. And so you would use software architecture techniques to isolate the model. Remember I said one of the business things is how long is this going to live? If you want it to live a long time, there are software architecture things you can do that will help you modify the system. And the definitions are different, or expanded anyway. So security in software engineering tends to be cybersecurity. Somebody is trying to break into my system. Okay, I have a variety, or trying to inject malware. I have a variety of attacks, most of which I know how to at least detect or prevent. With AI, now all of a sudden I can have attacks on the data. I can choose a model that's too slow. So latency becomes a problem if I have the wrong model. So the definitions of what I'm looking for are going to be different, bigger, broader. You're not losing anything, but you're gaining stuff. And if you look at the processes that a AI system goes through, you have the circle at the top, which is the standard sort of code, test, code, build, test, deploy. They'll get to that, right? So you write you have an assignment, you write it, you run it, it produces the correct output, you turn it in, you're happy, everybody's happy, you get a good grade. If you're building a real system, you write part of it, somebody else writes part of it, a third team writes a different part, you need to put them together. That's called the build process. Things can go wrong. Then once you get it built, you have to test it. Does it do what it's supposed to? Does it have the performance that it's supposed to have? Then I need to put it into production. I need to deploy it typically into a cloud. I need to set the security settings correctly. And it may be that it's a popular thing, and so I have multiple instances in the cloud. Again, if you haven't talked about these things, you'll get to them. And so all that is the top circle. And then when I'm operating it, I need to monitor how's it doing. So there's a job description for somebody called site reliability engineer. SRE is another acronym. But if something goes wrong and you have a system, you're a Google or a Netflix or an Amazon, you have a system that you want to be running all the time, 24/7, then if something goes wrong, you want somebody to call. And so one of the responsibilities of the first responder is they have a pager, or I was told people still use pagers. I don't know. Pagers seems kind of old fashioned, but anyway, they have the equivalent of a pager, maybe a SMS. No, SMS not. SMS is not a reliable delivery system. They have an RCS or something. Anyway, they have a device. Device buzzes. It turns out it's 3 o'clock in the morning. You're fast asleep. And it's your responsibility to get the system working again. That happens during operations. So there has to be part of the system that monitors that so that it knows there's a problem and so on. Okay, and it's the responsibility of these first responders to do that. And that's all the top circle. That's still true with AI systems. But what happens at AI systems is you have the bottom half circle, and there are more things to do. More things equates to more time, equates to more personnel, equates to management saying, God, we're spending a lot of money on this system. Maybe we ought to cancel it. And that goes into the 80% that don't go into production. Okay, you're running over budget. So one of the things you should learn somewhere along the line, and not in this class probably, but in general, is just business concepts. Terms like return on investment, time to market, okay, those kinds of things, because those end up driving what you'll do as a software engineer. Learn how budgets are put together. Okay, who is going to pay you? Right? I mean, what you'll get is a charge code. How does money go into that charge code? How is your time allocated so that you're not supposed to be working 120% of the time or 80% of the time? Okay, I mean, all these things are kind of peripheral to the job of a software engineer, but it's awfully useful for you to know these things. And so that's sort of a sidelight that you could do. But in any case, when you do an AI model, you have other things you need to do. You need to build the model, and you need to test it. You need to package it in such a way that it can talk to the rest of the system. These are all additional activities. And so preparing the data, oh, question, yeah. Yeah, good question. So for those that didn't hear, the question was, how do you deal with subsystems in general? Is AI a special case of that? And a good example is hardware. Let's suppose you work for Siemens. Okay, Siemens makes systems for trains. They make a lot of things, but they make systems for trains. System for trains has an engine and it has software. They build the engine using particular hardware, using particular processors. The software has to know about that. And so historically, there was a problem that the hardware people would design their processors. So at one point I did some work for Robert Bosch, and they were talking about choice of processors, and this processor was 1 cent less than that processor, and I'm saying 1 cent, who cares? They said, you're making 1 million of these things or 10 million of them. All of a sudden you start to care. So historically what happened is that the hardware people would design the processors, and the software people would have to live with it. Same kind of thing historically happened with AI systems. And so the AI people would be over here, the software engineers would be over here. And so what happened with the hardware, and that applies to AI, is a process called co-development. Even though you have individual teams working on each part, they need to collaborate closely. So the hardware people will say, we're going to make this decision. Does that impact you? And the software people would say yes or no. Or could you change it slightly? And so not only do you have to collaborate, but there has to be somebody on the software side that can understand, in this case, AI, or in the hardware case, the AI, and vice versa. So there has to be somebody to ask the question, is this going to impact you? So there's something called co-development, which uh, uh, applies to hardware and software, but also applies to AI. So that's a good question. Yeah. I think this, okay. So the question is how mature is AI development? And I think the answer is the latter. That, as people, so one of the problems I identified was this problem of education and the problem of building teams. So now project, you're a team that's worked on an AI system, whether on the software side or the AI side, and now you get assigned to another system. You bring the knowledge that you've learned from that collaboration. And so I would say that the collaborative part of it is going to grow as opposed to where it is now. Yeah. Okay, so who gets in charge of the team? Uh, um, uh, so at the moment, What I would say is that the more, so you're not going to be put in charge until you have experience. Well, but the decision comes from whoever's in charge. So I would say that you're not going to be put in charge unless you have a reasonable amount of experience, right? You're not going to ask a recent graduate in architecture to build you a 10-story building. So they have to, in essence, apprentice. Not called that anymore. So the people that have the most experience at this point are the software people. So I would say at this point that the lead in these kinds of things is going to come from the software side. I would say in 3 or 4 years that will change. And again, to use the analogy from hardware, what happened to the hardware? The hardware came first. Software was an afterthought. And all these companies, again, when I was working with Robert Bosch, one of the things they realized, which is why I ended up working with them, was that they were really a software company, not a hardware company. Uh, um, and so the realization, so the realization of software was after the realization of hardware. But what happens in the meantime is the hardware people get promoted, and they end up being a director of some sort, and they bring their background as hardware. So I would say the same thing's going to happen with software with respect to AI, that the software people will get promoted. The AI people will come along and say, how can you do that? But, so that's a prediction. So take it for what it's worth. Other questions? Okay, so the steps are you'd have to prepare the data. Again, coming from a variety of sources, you have to deal with missing data, and you need to keep track of all this. You have to develop the model, so you have to train the data, and there are steps involved in that. You have to test the model. So the model gets tested independently of the system, like a unit test, and then gets tested as a portion of the system, as a system test. And then you have to, somebody has to say, or the system has to say, it's okay to go. Okay, and again, that depends on the domain you have. And each one of these activities has its influence on quality. Okay, the data is messy. Data is always messy. If it isn't messy, there's somebody's fiddled with it. So there are missing data. There's missing data. There are transposed digits if it's something that somebody manually entered. There's a distinction between what one sensor tells you and what a different sensor tells you. I go to the doctor. He does my blood pressure. Every time he does it, it's different. You know, there are a lot of variation in the world. Okay, so data is messy. It has to be cleaned. You have to take care of missing values. You get outliers, things that are just probably wrong, but you don't know for sure. So where did this piece that's out there come from? What happened to it? Uh, Model building says I need to train and select the features, and then the test for these ethical things and data distribution. There are lots of tools. Okay, and so there are tools for data cleaning. There are tools for data lineage. Where does the data go? There are tools for model choice and packaging. Uh, not, so one of the things that happens with tools is that you start using a tool, and then the company goes out of business. And there you are. You now have to change. Or you start using the tool, and the company is acquired by somebody else, and they change the interface to the tool. Okay, I'm sure you all have experience with changing interfaces. Ingo was complaining about they changed the interface for this thing since yesterday or last week, or I mean, that's the world. And so achieving quality in AI systems is more difficult than a non-AI system because there's more involved. It's not that there's anything more inherent about the quality in AI. It's just there's more of it. And there comes a point when quantity affects quality. And you can still characterize it by quality attribute achievement. But so the quality attributes for software architecture are reasonably well understood. There are a set of known techniques for dealing with it. There's some for the data. I mean, some of these statistical techniques will fall into that category. Some of the data addition will fall into that category, but the notion of quality attribute in terms of data and its impact is not as well understood as it is in software architecture. So just to summarize this, uh, you need to worry about how do you achieve quality, and these are causes of failure. You have to worry about interdisciplinary teams and have built into your organizational structure the idea that it takes teams a while to get to the performing stage. Uh, you have to recognize that there's uncertainty. Statistical means uncertainty in all of these. And over time, I think the percentage of AI systems as people gain experience will in fact grow that are acceptable. Because people will gain experience in some of these problems and they'll know how to deal with. And as Ingo mentioned, we wrote a book. It's going to be published early next year. If you're nice to him, he may let you read a copy. In any case, you can order it on Amazon. At this point, it'd be a pre-order. And there were several other authors. So one of the issues in writing a book is that Ingo is in Germany, I was in the US, and two authors are in Australia. So if you do the time zone math, it's impossible to have everybody on the phone at the same time. So we managed. Okay, other questions about the AI portion? Okay, let me shift gears and talk about. Well, it's not bad timing. Talk about what it's like to be 60 years in the business. So first of all, as I said, I got a degree in mathematics. I had taken a tour and seen a computer, but I'd actually never programmed anything. Uh, uh, and I got hired as a programmer. They gave me what they called the pulse test. He's alive. And I got hired. Uh, and these are some reflections. Whether they apply to you or not is not, I can't say, you have to decide. But I was always very opportunistic. I did what seemed like it would be fun for the next period of time. I never had a master plan. Some people have master plans, I never did. So the first lesson is that the environment matters. And what do I mean by environment? I mean, what resources does your organization have? What personnel does your organization have? What are the goals of that organization? And ideally, they align. So if you're an academic, uh, your goal tends to be, I want to be recognized outside of my home institution. If you're working as a programmer and you want to build a reputation in some sense or another, it's the same kind of goal. Okay, if you look at the industrial-based conferences, speakers are either consultants or they come from companies you've heard of, the Googles or the Netflix or the Amazons or the Microsofts. Okay. You tend not to get somebody. So if you're involved in a startup, going to a conference is expensive, time consuming. I can't spend the time, more or less. Uh, so the first lesson is that the environment matters. I spent 15 years at the University of Rhode Island. was a good school. I mean, I taught, uh, but I didn't get a lot of external recognition. And then I gave up tenure, moved to Carnegie Mellon. And 2 years later, I was given a keynote in Milan. They pay attention to where you're from. And if you're in the computer science business and you're from Carnegie Mellon, it makes a difference. Or TUM, as far as that goes. Second lesson, collaborators are important. The days of the lone ranger, I don't know if that means anything here. The days of the solo scientist working in the lab, coming up with a brilliant idea all by themselves. I don't know that that ever happened. Certainly, it doesn't happen in the computer business, as far as I know. Yeah, and so you need to have people to work with, and the people you work with ought to be people you trust. They ought to not be clones of you. Right? They should have independent ideas, but they should be tolerant. Okay, there's a lot of give and take in terms of having collaborators, um, but that's an important element. And I didn't count them, but it must be well over 100. There are a few papers I've written by myself. Uh, the books I've always had co-authors. But if you get a lot of people, it gets to be self-defeating. So at one point I was involved in a documentation, writing a book on documenting software architecture. And the second edition had 8 people. So everybody wants to say something. Everybody has a point of view. You have to consolidate these points of view and make something that everybody agrees to. That takes time. So the production sequence on that particular book was about twice as long as the production sequence on the other books that I've written, just because of the number of people. So I like 2 or 4. You know who you're trying to talk to. If you're talking to academics, then they want evidence and they want uniqueness. So the thing you don't want to have happen if you're an academic is you do some work and somebody says, somebody over there did that 2 years ago. It's got to be unique. And if you have aspirations of getting a PhD, what I've been telling people is that you end up knowing more than anybody in the world about something that nobody cares about. So you know more and more about less and less, which is okay, because the goal of getting a PhD is to get a PhD, not to change the world. Changing the world comes later. There are a few examples of people who have written revolutionary PhD theses. Now his name escapes me, but the guy that invented graphics. Mm-hmm. Uh, I wouldn't give him total credit for HTTP. I mean, he was part of a team. Uh, uh, you know, um, and even maybe Denning. Can't remember his first name. He invented the Google founders would be good, yeah. But again, you got they were not the first search engine. So there were other search engines. There were other search engines involved in Facebook. I mean, there were other engines. Facebook was not unique. Uh, Google was not unique. What they learned how to do was how to do scale. But anyways, so academics like uniqueness. So in this case, the uniqueness would be the scale. And with Google, the uniqueness was ultimately they figured out how to get money out of it. Um, if you're talking to somebody from industry, then they want clarity and applicability. Is that something that I need to worry about? Because they have a very narrow focus. So if you're talking to an industrial person, They're working for a company. They have a particular responsibility. They kind of want to pay attention to what else is going on, but they're pretty much with blinders. And that's true of academics as well. If you're talking to a student, you want to give examples. Your students like examples. Show me how this works. And if you have different audiences, you need to, pitch your message appropriately. So I've written a bunch of books, and they're all targeted at senior level or early graduate students, or maybe early career professionals. So you look at this book that Ingo and I and the other people just wrote, and the message is you're now part of an interdisciplinary team. You're the software engineering on that team. How do you talk to these people? What are they talking about? Or you're the data scientist on this team. How do you talk to the software engineers? What are they talking about? And that's sort of one of the messages of the book. And then when you write a journal article, you got to be unique. The other thing that's the lesson, or another lesson, is that the computer industry has changed radically about every 10 years. Can't say exactly 10 years. But when I started, it was mainframes, not as big as this room, but air conditioned at least. So I was in the California desert. You would go visit the computer and you would say, "How you doing?" And you would cool off. In the 70s, networks came in. In the 80s, you got personal computers, you got direct manipulation. All these have software effects. In the 90s, we got the World Wide Web. Again, significant difference. In the 2000s, we got the cloud. Again, significant issues. 2010 was DevOps. 2020 are clearly AI. Can't open your mouth without saying AI. 2030, if I had to guess, I would say it's probably quantum. So what happens is that these changes are going to impact you in whatever career you end up doing. And so you need to pay attention to them. A good place to look is the Gartner hype curve. I don't know if you, so look up the Gartner hype curve. What it says is that a technology comes out, everybody gets real excited about it, it rises to the top of the hype curve, and then people start to use it and you get in diminishing returns, and everybody says, oh, that stuff is AI. I mean, most of those systems don't get into production, let's do something else. And so it goes down. And then what happens is that people learn how to use the technology and it sort of levels off. And so there's a hype curve for virtually every technology. But the reason you would look at it is, what are the upcoming technologies? What do I need to pay attention to? And you don't have to pay a lot of attention, but you ought to at least know the terminology and so on. Because otherwise you get out of date. I know an awful lot of people that used to be very good help desk, used to be very good operators. And those kinds of jobs are mostly gone. Now, I also have a problem with what AHD something anyway. I have attention deficit, so after a couple of years, you get tired of what you're doing and you want to move on. So my PhD was in theory of computation. I was trying to explain that earlier. You don't want to know. It's more and more about less and less. And then the other part of my PhD was the work that I was doing, not the research. And so I built an operating system. So I learned about operating systems. Actually, so getting a PhD will teach you about research. Building an operating system, I still live on that. So I mean, I can talk about concurrency and all those things from knowledge. I got involved as a consultant to a research lab. So again, opportunistic. I took a pottery class, ceramics. You know, you sit at a wheel, you make things that are going to last forever. And they literally do. You can go to the museum and see people have done this. Somebody at the next wheel happened to be a director in a water quality lab for the local Environmental Protection Agency. It wasn't local, the US. And he said, we just bought a computer. We bought it for this particular purpose. You suppose we could use it for other things? I said, sure. Let me tell you how. I need to learn something about your domain. So I ended up working with them for 10 years. And what they needed, one of the things they needed was a database management system. So another thing they needed was a statistician. I couldn't do that, but you know, but you had to build the database management system so that it was compatible with the statistical systems that they used. So I built a database management system, and that got reflected in some papers and this and that and the other thing. User interface systems. Part of building this database management system was I had real customers. All of a sudden, you know, the idea that you should design your system so that people could use it got to be important. And so I got involved in user interface stuff. And that sort of segued into software architecture. And then when I went to Australia, I got involved in DevOps. And now all of a sudden I know something about AI, which is kind of a shock to me uh, because I pretty well ignored it up to now. And you've heard everything I know. So at least I can give a talk. And so if you count that, that's 7 topics in 60 years, you know. So every 7 or 8 years, I get involved in something else. And a corollary to that is don't be afraid to take risks. So changing field within software engineering requires convincing a new community that you have something to say. If you go talk about how to be a good, you know, help desk person, nobody cares. Okay, if you go talk about how to use AI to do help desk, somebody will care. You have to know what you're talking about. You get people that are not too nice to you. So you need a thick skin. And for me, the process takes a couple years. So maybe you coast on something for, you know, I'll do this and learn something on the side, or maybe you just say, I'm not going to do this anymore. I'll learn it on the side. I'll just make that my thing, but it takes a couple years. So I took a course in theory of computation when I was in graduate school. It's the only software engineering course I've taken. You get into sort of embarrassing situations. So the first assignment I had at Rhode Island was to teach a compiler course. What did I know? So I did a lot of reading and found out what I could, and it turns out that compilers are based on formal languages. So I understood formal languages. It was kind of like theory of computation, so I taught a bunch of formal languages. At some point about midway through the semester, somebody raised his hand and said, sir, what relationship does this have to the catalog description? So you have to, you know, be prepared to take a few bruises. But you know, there's a ton of information out there these days. So back when I taught compiler theory, the next year somebody wrote a book on compilers, so that I actually had something to work with. Uh, um, but these days, I mean, you know, if there's something you're interested in, there's a YouTube video, there's a description. You know, people like IBM and Microsoft write very nice overview documents. You know, if you get involved in the actual details of it, there's Stack Overflow. Okay. So I would ask my students, I don't anymore, but I used to ask them, you know, so you're doing your assignment and you have a problem, and what do you do? And the answer would always come back, well, we have to find the root cause. That's terribly wrong. What you do is you take your error message, you paste it into a browser, you hit click, and somebody has found that error message and tells you how to fix it. Okay, so root cause analysis is not something that people typically do. But you can learn, you can teach yourself virtually everything. Okay. And it helps if you have somebody to bounce it off of. And then finally, this is for Ingo. Avoid management at all costs. And people, you look at a career path and you say, okay, I'm going to get a job in a company and then I'm going to get promoted. And instead of having colleagues, I'm going to have 5 reports or however big the team is. And then I'm going to do a good job and I'm going to get promoted and have 25 reports, So it's a different set of skills. It's not that it's not important. It's just different. Okay. And I know of good technical people who get swallowed up into management. And they can't make the same impact because they don't have the right set of skills and they lose their technical credibility. It's also a time sink. One of my metrics of the importance of people is how much time do you spend in meetings. So if you spend 80 or 90% of your time in meetings, you're a manager. I don't care what they call you. You have to spend a certain amount of time doing work. But that's different than being a leader. So I once traveled with somebody who went into an organization. He said, okay, show me your org chart. Got the org chart. He said, okay, now tell me who knows about, who's the leader in each one of these areas. And sometimes it was a manager and sometimes not. Okay, so every organization has leaders and they may or may not have managers. Okay. So when I went to Australia, the woman that recruited me offered me a job with no direct reports, no budget responsibilities, and no reporting to upper management. It took me about 30 seconds to say yes. But then what happened is after about 1.5 years, she went off to do something else and they told me I was in charge. So that wasn't nearly as much fun. But not being in charge means that sometimes you get assigned projects that aren't ideal for you. That's one of the costs. So good luck to all of you. I've enjoyed my 60 years in the computer business. I can't. When I graduated with a bachelor's degree, I interviewed in 2 types of organizations. One was the one that I ended up with to be a programmer. The other was to be an actuary at an insurance company. That was one of the options if you had a math degree. I'm so glad I chose the computer. So anyway, thanks for your time.